In this YouTube video, Uncle Doug talks about the impedance ratio of output transformers. And I highly recommend this. It's a very, very nice video. And he's done a few others, as also has El Paso Tube Amps. I also recommend some of his. But in this, after showing you how to measure various things, especially the impedance ratio and the turns ratio of output transformers, Uncle Doug concludes that that the best thing is just to go to the technical manual, to the tube manual, and look up the impedance that you need to use with your tubes. That don't try to figure out all of the nuances of output transformers. Just take the value that the manufacturer publishes for the transformer you're using and the value that the tube manufacturer tells you for the load impedance for the tube that you're planning to use. And that's very good advice. And the reason is that, frankly, tubes, output transformers, and speakers as well are, well, let's just say there's a lot of little detail, and you can get completely, well, if all you did was go into the swamp to pick a flower, you're going to wind up killing alligators and draining the swamp. So better to stay at a fairly high level on this. But I'm not going to take Uncle Doug's advice, though normally his advice is really good. And in this particular case, I think it's excellent advice, but I'm still not going to take it. Why? Because I have not found a decent video on YouTube that explains all of the reasons that tube amps sound different from transistor amps. So that's what this video is going to be about. So here is a little bit of what I propose to do here. And I'm actually, I saw a video a little earlier from D-Lab in which his granddaughter is taking him to task for shooting the introduction after he's already completed the work. And I'm not doing that here, but I will tell you that I have done a lot of this stuff before, so I kind of know how it's going to turn out. It's just that it was done a long time ago, so if my memory serves me correctly, I'll get the same result that I'm going to pretend that I'm going to talk about now. The big issue with all amplifiers is that they contain nonlinear characteristics, and that means distortion. Now, some people like distortion, and I did some videos a couple of years ago on human perception with audio and hi-fi and music and so on. For example, most guitar amplifiers are deliberately designed so that you can distort the sound in many ways. Most hi-fi amps are designed in a way that minimize the distortion. So somewhere in that range is where pretty much everyone and all our music falls. And with tube amps, there are three areas where that distortion comes from: speakers, transformers, and tubes. Now, there are other things that can cause distortion, including the power supplies that I will talk about briefly, but basically it's speakers, transformers, and tubes. Now, speakers are common to the tube amps and transistor amps, but transformers and tubes, of course, are not. You can put a transformer in a transistor amp, but because the transistors don't behave like tubes, you're not going to get the same sound. So what we're going to do is look at speakers, the fact that their impedance is not constant. In other words, if you look in the tube manual, as Uncle Doug suggested you do, you get one number for the load resistance. Well, unfortunately, the load resistance doesn't stay in one spot. It changes with frequency. The second thing is, with the speaker, its impedance is reflected through the output transformer back to the tube. And by the way, it's reflected the other way as well, but people don't normally talk about that. In other words, things like the damping factor of the amplifier is affected by the impedance that as it changes with the speaker. We may get into that, but probably not. With respect to transformers, there are 4 areas that contribute to the distortion, or maybe I should just say the sound of a tube amp. The first is what's called hysteresis. All magnetic systems have some type of hysteresis, and as you try to transfer an alternating current through a magnetic system, you get variations. It acts differently when you're going in one direction than when you're going in the other. A little bit like those treadle things outside the rent-a-car places, that if you drive in one direction, you're fine, but if you try to back up, and that is a form of hysteresis. Second thing is something I've talked about in some previous videos, and when I get to this, I'll refer to those videos. Leakage inductance. What that really means is losses in the transformer. In other words, you put a certain amount into the primary, for example, and it doesn't show up in the secondary. Instead, it gets lost in the transformer. That's leakage inductance, and it is modeled with an inductor in the circuit models. The third thing is the autotransformer action, especially in push-pull amplifiers. A lot of times people try to explain things about push-pull amplifiers, and they never mention the fact that one side of the push-pull primary is interacting not just with the secondary, but also with the other side of the primary. We'll talk about that. And then, obviously, there are interactions between the primary and secondary. Now, here are in keeping with Uncle Doug's simple philosophy, we're going to try to keep this thing down to as little math as possible. I'm hoping to stick just with Ohm's law, and by that I mean Ohm's law for alternating current that uses impedance, not just resistance. We're mostly going to use graphical analysis because I think a picture really is worth 1,000 words. And finally, everything we talk about, we're going to try to back up with an experiment, sometimes more than one. We're going to look at speakers using the analog discovery impedance analyzer. We're going to look at transformers, once again using the analog discovery. And we're going to look at some tubes using the Tektronix 570 curve tracer. So, stick with me if you're interested in really understanding, and don't already understand, why tube amps sound different. What you see on the bench is the Analog Discovery 2 running a scan, an impedance scan of this Panasonic speaker. Let me stop this. If you're interested in more on the impedance analyzer, you might look for these videos, Tom Tech Test 190 and 191. But the particular speaker that we're looking at has a nominal impedance of 6 ohms. So, well, it's not going to focus there. Maybe it will in a second. There we are. You see it's a 6 ohm nominal impedance. So let's go look at what we actually got on the waveforms display, but before we do, I'm going to stand this speaker up because that way we can run it in the other position to get a comparison. And what I'm trying to demonstrate is that the environment of the speaker determines to some extent the impedance it presents to an amplifier. So let's go look at waveforms. So here's the display. This is the waveform software that comes with the analog discovery. Let me move this out just a little. And what you see is from left to right 100 hertz to 100 kilohertz. On the top display is the impedance of the speaker, and on the bottom display is the phase of that impedance. You notice that it starts out at, well, let me move this over just a little bit. Here we are. It starts out at about 15 ohms, goes up slightly, then goes down, rises again, goes down, and hits about, somewhere around 8 or 9 ohms, rises again and comes back down, and then eventually winds up at around 40 ohms or 35 ohms at 100 kilohertz. So that's with the speaker laying face down. Now let's run one with the speaker standing up. Now you'll notice that the peak is more pronounced at the roughly 220 to 230 hertz. The peak is more pronounced. Now this is not a woofer, so it's not supposed to perform real well down here at the low end. But the reason that I chose this speaker is partly because it exaggerates the effect that occurs in all speakers, especially at the low end, because this is not a particularly good low-end speaker. By the way, this speaker comes off a Panasonic home theater that has a separate subwoofer, and most of the low frequency energy is diverted into that subwoofer. But nonetheless, you see the difference, and you see how the phase changes dramatically. Now let's try another speaker. Okay, what you see here is a COS model M85 Plus. This is a little bit better speaker. Notice that it is a nominal 6 ohm speaker also, if I remember right. Yeah, 6 ohms. And notice that it starts out about 6, goes down a little, comes up a little, has a peak at around 1.5 kilohertz maybe, at nearly 15 ohms, then drops back down, and then eventually winds up back at around 15 ohms, around 100 kilohertz. Now, once again, I'm doing this speaker with it laying down on the bench. Let me stand it up in its normal operating position and run it again. And you notice in this that it has changed the impedance slightly. This peak is very slightly smaller, but it basically is the same response that we got earlier. So let's take a look at that speaker. Here is the analog discovery, and this is the COS speaker that we're working. It's a small bookshelf speaker. Once again, it's not real quality. But I do have some pretty good speakers, but I'm not really going to use those because, quite frankly, these cheaper speakers actually illustrate my point better. The better the speaker, the less it changes with frequency. So, but a bookshelf speaker or a small speaker like comes with the home theater systems, or most, let's say, cheaper speakers, speakers that cost under $150 or $200 a pair, generally have this characteristic. Now, as you get higher in cost, you get to a point where the speaker might be a better quality and a little flatter response, particularly speakers that have been especially engineered to present a flat response over a wide frequency range. I have a pretty good set of Klipsch speakers that are fairly flat. They still have peaks though. So what we have seen is that the impedance of speakers changes with frequency. I think we all knew that. Also, that impedance change is reflected through the output transformer, and it's that reflected impedance that the output tubes see. So let's talk next about transformers. Initially, we'll take a quick look at hysteresis, and then later when we get down to tubes, we'll talk a little more about the effect of hysteresis on the tubes. Finally, or next, we'll also do leakage inductance, talk briefly about autotransformer action, and then especially talk about the primary-secondary interaction. What this picture shows is what is called a hysteresis loop, or a BH curve. BH just refers to the flux density versus the magnetic field intensity. Don't worry about it. It doesn't really matter. The point is that if you have an electromagnet like the primary of a transformer, and you start with no current, and you drive current into that primary, what will happen is the magnet that is created in the core of the transformer will follow this curve. Notice it's not a straight line. It doesn't just go straight up like a resistor would. It goes up to this point, at which the core becomes saturated. Then, if you begin to reduce the current, and by the way, the current is also the same as the magnetizing force. In other words, it's along the x-axis. As you reduce the current, it doesn't trace that same line back to zero. Instead, because of residual magnetism, it comes down to this point. When you are back to zero on current, you are not back to zero on magnetization. And that is sometimes called retentivity. You don't need to remember any of these terms, but in case you see them, you'll kind of know what they refer to. Then, as you reverse the current and begin to drive current in the opposite direction, it will come down until eventually, at some point, it will cross the x-axis again. In other words, there is no flux in the core. And that is, the measure of that is called coercivity. That is how much you can coerce the core. Then as you continue to drive negative current, you come to the negative saturation position. And by the way, these are not necessarily the same. That is, the negative may not be exactly the negative of this or the inverse of this. And then as you increase the current from most negative current back to zero current, you will come to this point, and finally you'll reach this point. Notice that you now are at a point that is different from where you started. And in fact, you will never go back to where you started because of residual magnetism. The only way to get back to the 0 point is to demagnetize the core. So once you have gone through a magnetization cycle, from then on, the core remains at wherever you left it, usually at either this point or this point. So what's the point of all of this? Well, the reason is, if we take Uncle Doug's advice and we look, for example, I'm going to take a 6L6 because I happen to have a pretty nice pair of matched Tungsol 6L6s that I'll be looking at later in this video, or maybe in part 2. I think it's going to be a second part. it says the plate resistance is 22,500 ohms at 250 volts, or 33,000 ohms at 350 volts. But notice that it recommends a load resistance of 2,500 ohms at 250 volts, and a load resistance of 4,200 ohms at 350 volts, and this is with fixed bias. If you're using cathode bias, those values change a little bit, especially the one for the 300 volt cathode with a 300 volt plate voltage with cathode bias. So, okay, you got a number. Suppose that you wanted to use 350 volts and 4,200 ohms. So, what would you do? Well, actually, I think what I'm going to do is use the 2500 because that's the one that the tube manual uses. So out of the tube manual, this is RC15 tube manual, RCA tube manual, which, by the way, you can download from AmericanRadioHistory.com. For the 6L6, you notice the load resistance is shown here. This is blown up a little bit. What this actually, to show you a little more, is this is a 6L6 with a plate voltage of 450 volts and a load resistance of 2,500 ohms. I hope I'm not confusing you with all these numbers. This is just to illustrate a point. So you draw a load resistance line like this, and if the world were perfect, you could, from that load line, you could determine how this 6L6 would perform. Unfortunately, it's not quite so simple. I've drawn a few other load lines, for example, 5,000 ohms and 2,000 ohms. Now, why do I do that? Well, this is a chart from a book called Fundamentals of Vacuum Tubes, and you'll see it in lots of, you can see the Radiotron Designer's Handbook and some others as well. It's fairly well known. In this case, it is the load impedance on the tube and the percent distortion. Notice that if, and this is the power output, by the way. So as the load resistance goes up, the power output goes up. But look what happens to the distortion. As you raise the impedance, it begins to drop the total distortion. Now that's because this is the second harmonic distortion. This is the third harmonic distortion. Now, you can get rid of second harmonic distortion using push-pull, and we'll talk about that much later. But it's hard to get rid of this third harmonic. And so, what you might want is to operate down near this low end to get less third harmonic distortion, or closer to 7,500 ohms to get lower second harmonic distortion. So what's the whole point of this? Well, it is that unfortunately, due to hysteresis, you don't get a straight line. You get this. If you have a transformer, this is the load line. In this case, is for a triode, but it would look the same for a pentode. Notice that this is the operating point. But as soon as the tube begins to put current through the output transformer, you go to this line. So you might go up something like this to this point. And suppose at that point you reverse the current and begin the excursion toward the negative half cycle. Well, you come down this side. You get to this point where the plate voltage is the highest, and which means the grid voltage has the plate current is the lowest, and then you go back up on the other side. Well, if we use the value from the tube manual, how do we compensate for that? Well, the reality is that this value of 2,500 or 4,200 ohms is a compromise that the tube designers have taken into account by looking at things like this and trying to balance power output with distortion so that you get the least distortion at the most power output. And so, for example, for the 6L6, they recommend 4,000 ohms or 4,200 ohms at a plate voltage of 350 volts. That would be about this point. And by the way, this is just a generic chart. This is not the actual chart for a 6L6. But that would be this point. Notice that you're not getting as much power output, but you are down here a ways on the distortion. And especially on the third harmonic distortion, you're way down here. So that might be the best operating point. But if you haven't guessed it by now, this is very complicated. In fact, there is really no way of doing this the old way. There are modern instruments that do allow you to test a lot of this stuff dynamically, but they're rather expensive, they're very rare, partly because nobody does tubes anymore, and therefore they don't sell them in volume like they do oscilloscopes, and partly because they are so specialized that the market for them is very small, and generally they only exist in labs. But let's not give up. Let's move on and see if we can now take a look at the effect of hysteresis and of the characteristics of transformers to at least visually see what goes on inside a transformer when you connect it to a speaker. So this is the load characteristic of a triode, and by the way, this picture comes from a textbook or a handbook called Radio Engineering Handbook. In this case, it's page 365 of the second edition. There you can download this book from the AmericanRadioHistory.com website, and there are 3 editions there. This is the first, and I'm using it because it's one of the early ones. So they expect you to draw a load line. How do you do that? Well, one way to illustrate that is, let me find this is for a triode. You can see on this, what you do is you pick your plate voltage. In this case, this is a 6J5, but it doesn't matter. You pick your plate voltage, and then you either decide on the load resistance you want, or you decide on the plate current that you want. So let's assume we're using the Uncle Doug method, and we're using the resistance out of the tube manual. So in this case, this is a load resistance of 25,000 ohms. At least that's what it says. I have not checked this, by the way, for accuracy, because I'm just illustrating, but in a minute I'll show you that you do need to check these. So you start at 350 volts. That's one end of the line. And then you take that value, 350, which is EB, and you divide by RL. And that gives you the current at this end of the line. And then you just simply draw a line between it. Now, as we've already seen, that's not what the tube is actually going to see. The tube is actually going to see a transformer, not a pure resistor. I said earlier that that you need to check things. This is from a book called Fundamentals of Vacuum Tubes, I think is the... Yes, Fundamentals of Vacuum Tubes. It's from the McGraw-Hill series. Quite a good book, but it does contain errors. For example, this drawing of a tube and a load line is wrong. They show 3,900 ohms. It's really 5,000 ohms. And you can tell that if you just draw the line out to the ends and compute this line violates Ohm's law. So the professor should have had his grader check the book before he sent it to the publisher. But that's just an illustration of you need to always be careful and check, because just because it's published by an expert doesn't mean that it's necessarily correct. It's good to cross-check. For example, I talked about using this book called Radio Engineering Handbook. But you might choose instead to look at the Radiotron Designer's Handbook, also available on the same website. So, as a cross-check, and I use both and others as well. So, let me show you how to find these books on that website. Here is how you can find some of these books that I'm talking about. If you go to AmericanRadioHistory.com, the address you see right here, and click on the main menu. Now it says home page, but when you put the cursor over it, it'll say main menu. Click on that, and then go over here to the right and click on bookshelf. Then, for example, to find Radio Engineering Handbook, we scroll down, and over here on the left, we find Radio Engineering Handbook right here. Click on that, and you find that there are 3 editions. There were a total of 5 editions, at least according to this site, but they only have 3 of them uploadable. And the one that I am working with is this first one, Radio Engineering Handbook, 2nd edition. You click on that, and you get the downloadable PDF. So you can either read it, or you can download it and print pages out, however you would like to. Well, this video has gotten way too long, and so I'm going to have to break it into at least 2 parts. So let me just tell you what we've done so far. We have looked at speakers. We have talked about transformers. We are now in the next part. We will look more at transformers and actually do some measurements, particularly with regard to primary and secondary interaction. That is the effect of things like the speaker impedance change on the tube that's driving the output transformer. If you're not familiar with terms like leakage inductance and autotransformer action and so on, you might want to, in addition to the 190 and 191 I referred to earlier, you might want to look at my number 186, that is Tom Tech Test 186, which talks about output transformers in tube circuits, and especially if you're not familiar with how the turns ratio relates to the impedance ratio and things like that. Also, I think that video I talk about how you can measure leakage inductance, which we will not do in this video. We won't repeat, but what we will do is we'll refer to it when it becomes important. So as you can see, I'm passionate about this subject. It's something that was one of the first things that I was really interested in when I was a very young 10-year-old kid. And although I got out of the field at one point because I, quite frankly, got tired of conceited rich people, later, after I finished my bachelor's and master's degree, I had a little time and a little money. And so, actually, while I was working on my PhD, I went back into this. And at that point, as you can tell, I really got into it in depth. And I don't plan to try to make you a PhD in tube output stages. But what I would like to do is let you know a little bit about what to look for and where to look for extra information on it, so that you can explore this subject to whatever depth you would like to. But for now, let's close this video, move on to video number 2 or part 2, and in the meantime, have a nice day.